Okay, today we're going to talk about how to use trapezoids to estimate area under a curve. We have already used rectangles and using a left Riemann sum and a right Riemann sum, and we've done midpoint. But today we're going to talk about how we use trapezoids instead of rectangles. So let's talk about the integral from, it says let's look at the example, given the definite integral from 0 to 8 of x squared. Well, let's see what that graph looks like. We've got 0 to 8. I'm going to do 2, 4, 6, 8, only because I see they told me to use a trapezoidal rule with 4 equal subintervals. So 4 equal subintervals means that my delta x is going to be always b minus a divided by n. So my delta x is 8 minus 0 divided by the number of subintervals, which is 4. So my delta x is going to be 2. So I'm going to do 2, 4, 6, and 8. So we're talking about this area here. So the trapezoids are going to look something like this. Let's draw in red. Trapezoids look something like this. It's going to be here, and the next trapezoid is going to be here, and the next trapezoid is going to be here. So a little bit better estimate than a rectangle. Well, let's see. We also need to remember how to find the area of a trapezoid. So it's 1/2 times the height times base 1 plus base 2, where the height is always, the height of the trapezoid is going to be my delta x. So from 0 to 2, 2 to 4, 4 to 6, and 6 to 8. And the base 1 and the base 2 are going to be the two values of the function on the left and the right. So like with a right Riemann sum, we just use the right value. For a left, we would just use the left. But for trapezoids, we're going to use both. Okay, so I'm going to make a table. Let's make a table of values so that we can use them to find the area of the trapezoids. So I'm going to start 0, 2, 4, 6, and 8. The value at 0 is 0. The value at 2 is 4 because my function's x squared. 4 squared is 16, and 36 and 64. Okay, so I'm ready to make my rectangles now. So I'm going to start with the first rectangle from 0 to 2. So 1/2 times 2, that's the height, times base 1 plus base 2. The value of the function on the left plus the value of the function on the right. Then the next trapezoid is 1/2 times the height, which is the delta x, times base 1 plus base 2. So the value of the function on the left plus the value of the function on the right. And then the next trapezoid, the third trapezoid is that one was from 2 to 4, so this one's from 4 to 6. So my delta x is the same, and the value of the function at 4 is 16. The value of the function at 6 is 36. And then, lastly, my fourth trapezoid, 1/2 times the height, which is 2, times base 1 plus base 2. Okay, so here are my 4 trapezoids, and I want you to notice that they all have something in common. They all have a 1/2 times a 2, so we're going to go ahead and factor that out. And I also want you to notice that this 0 only appears once. This 64, let's fix that. That looks ugly. 64 only appears once, but the 4 appears twice. The 16 appears twice. The 36 appears twice. So when we factor out that delta x, that 1/2 times height, which is our delta x, then we only have the first value once, but 2 times the other values. 2 times the other values, and the last one only once. So with this little trick works only when you have 4, let's highlight 4 equal subintervals, when the subintervals are equal. Okay, so let's figure out what this number is to figure out our approximation. So 1/2 times 2 is just 1. So let's see, I got 8 plus 16 times 2 is 32. 2 times 36 is 72. And 64, I might have to go to my calculator. Let's see, that's 40. 40 and 72 is 40 plus 72 is 112 plus 64. 112 plus 64 is 176. 176 is my approximation. Okay, so I made trapezoids. Let's look at the next part. Is your answer to part A an overestimate or an underestimate? Justify your answer. Okay, so if we look at our picture, it is obvious that when we make trapezoids for this graph, it's going to be an overestimate. Let's think about why. I think it's because, so we have an overestimate overestimate. And I think it's because my function is concave up. Let's look at what would happen if my graph, let's go to the side. What would happen if my graph was concave down? If my graph was concave down, then I would be making trapezoids like this. That would be all under the curve. So it would be an underestimate. Okay, so the next question, it says, use your calculator to find the exact value of this integral. And does your value agree with your answers to part A and B? Okay, so let's go to our calculator and we're going to do math 9, integral from 0 to 8 of x squared. I'm going to find the real value, the exact value of this graph, of this integral. It's 170.6 repeating, which is less than our estimate. So we were correct that our estimate is an overestimate. Okay. So 1 and 2 are exactly the same. So let's go to number 4, where it's a little bit different. So in number 4, we are given the values for f on the table above. We want to approximate the area under the graph of f from -5 to 5 using 4 subintervals and a trapezoidal approximation. So we want to use trapezoids to approximate. So we got to remember the area of a trapezoid is, always remember, 1/2 times the height times base 1 plus base 2. And we are using 4 subintervals, but all we have is a table. We don't have a function here. All we have is a table. So we want to notice that our delta x is not equal, is it? So when our delta x is not equal, we are not going to do what we did up here, factor out the 1/2 times the height. We're not going to do that. When our delta x is not equal, we have to do each trapezoid separately, because the delta x is not constant. Okay. So I'm going to start with the first one, from -5 to -3. So it's going to be 1/2 times the height. Remember, the height is always your delta x. So my change in x there is 2. And then base 1 is 10 plus base 2 is 7. The value of the function on the left plus the value of the function on the right. Plus, and then I'm going to do the next trapezoids. So my delta x for my next trapezoid is 3 because it's from -3 to 0. So that's 3 units. And then plus the value of the function on the left plus the value of the function on the right. Okay, I've got 2 more. 1/2 times the height. So from 0 to 1, the delta x is just 1. So from 0 to 1, the value of the function on the left plus the value of the function on the right. And then my fourth trapezoid is from 1 to 5. So that delta x is 4. And then times my value of the function on the left plus the value of the function on the right. So we could use our calculator to figure out what this number is, or we could leave our answer just like it is. There's no need to simplify. We just need to remember that when we're given a table like this, that's the only information we have. So in order to find the approximation using trapezoids, we have to find the area of each trapezoid separately. Okay, so let's do one more just to make sure everyone's clear. A radar gun was used to record the speed of a runner during the first 5 seconds of a race. Use the trapezoidal rule. I'm going to underline what they're asking me to do. Trapezoidal rule with 5 equal subintervals to estimate the distance covered by the runner. So we know if we're given velocity and we integrate velocity, we're going to get our change in position. If we integrate velocity, we get change in position. So here they're asking us to integrate velocity, and which is not necessarily the total distance, but if the runner's not changing direction, then the change in position, your displacement, is going to be the same as your total distance. Okay, so let's do trapezoids. 1/2 times my delta x. I'm looking at my delta x and it seems to be 1. 0 to 1, 1 to 2, 2 to 3, and so on. So my delta x seems to be 1, so I'm going to factor that all out. And then I'm going to do the value, all the way to the left just once, 2 times every value, we already talked about y, 2 times every value in between in the middle, and then the last value only once. And that's literally it. So there's no need to simplify. If you simplify, it's okay, but there's no need. Okay, so that's how you do trapezoidal rule.